Hello, boys and girls. Welcome to class. I got a lecture for you. Hope you guys got your seatbelt on. We start time-dependent sources today. Well, we might as well cut to the chase, shall we? I think this is where the class gets by far the most interesting. And I think you'll agree once you get past the shock of the mathematics a little bit, but the stuff is awesome. Here we go. So what I want to do here is that I want to first start off with we want to start off with switches just to make sure that we don't want to be dealing with switches anymore. What we want to be dealing with is we want to be dealing with unit sources, and when we deal with unit sources, it makes it just nicer so that we don't have to deal with this stuff. So here we go. So we're going to start with the unit step source and a pulse source. So these sources, even though they're time dependent, we treat them as constants. So what we want to do here is that our goal here is that we want to simplify switches into unit step sources. We don't want it switches. Okay, so what we're going to do here is that we're going to define a step function. So a unit step function looks like this here. We define it as u of t minus t naught, and then this guy's going to be either 0 or 1. And so we typically say that for t less than t naught, it's 0, and then it turns on at t greater than or equal to t naught. This is our step function right here. And picture-wise, it's fairly obvious. So if I go here and I plot my function, which is going to be u of t minus t naught, and of course we're plotting this with respect to t, you'll see that the source then, what does it do? It goes all the way, and then right here, it jumps up instantaneous, and it steps up. So this value here is a value of 1, and this guy turns on at t equal to t naught, right? So then after this, we see that we now have a unit step function. So the way we do this here is that it looks something like this here. So, in a circuit with a switch, in other words, we have a voltage source that looks like this. And what we're seeing here is that we're going to turn this guy on and off by a switch here. And of course, this can either be, I should be very careful here. I'm just going to say that's my open. Okay, so this is the voltage of the open. And what you're going to see here is that you could imagine that I have my switch right here. So if my switch is in this position and then it moves in that direction at t equal to t naught, then what you're seeing here is that I can replace this thing, right, with either a 0 or a value for the voltage source. So for t less than t naught, and this is for t greater than or equal to t naught. Now the equivalent of this guy, as far as a step source is concerned, is then going to look something like this. We're then going to say that we have a source. And when does this source turn on? At t equal to t naught. So now I have my circuit that looks like this. and that guy turns on at that point. And we can clearly see that what we're seeing, that the value of this guy here equals this. That this will be 0 for t less than t naught, and this will be v source for t greater than or equal to t naught. So anytime we have a switch, we're going to use the u function, the step function. Now, another thing that we've been talking about and that we talked a tiny bit in lab, but we're really going to see this in the upcoming labs here, is that we want to produce a pulse source. So to produce a pulse, you know what? Let me write this differently. A pulse square voltage source, we will use 2 unit step functions. And the way we can do this here is that we can do the following thing. Picture-wise, what does it look like? It looks like this. So if I have a source, and you could imagine that it looks like this guy right here. And what I'm going to do here is that I'm going to say that this guy right here is going to produce a positive source. And then I have another guy down here that's going to produce a negative source. So I have 2 different sources. So what I'm going to see here is that the first source doesn't turn on till when? Until it reaches T naught. So at T naught, it goes like this. Oops, that's a little bit too high. It goes to about right here. Then it goes on. And so what you're seeing here is that I have my positive source that looks like this. Now I have a second source. Wait, let me be careful here. So this guy turns on at T naught. And then I have a second source that doesn't turn on till a time later on. Let's call this T1. But this time it's going to go what? It's going to go negative. And as it goes negative, it's going to look like this here. And so I have these 2 sources. So what I really have here, right? What I really have here is that I have the following thing, is that this I can model by 2 different pulse sources. So I have a source that does what? It turns on at T naught. So here's my source here. But then I have a negative source. So then this negative source doesn't turn on until T1. Oh, I'm getting my signs wrong. And then if I put these guys in series, then the open right here is what we call V pulse. So I have a pulse waveform. And the consequence of this picture then looks like this. So then I have my V pulse. It comes in, and what does it do? Well, it comes in, and at some point it turns on, and then it turns off. And of course, this is T initial, this is T1, and so now I have my step source right there. So I can produce these guys, which will be useful, very, very useful. Okay. So I just wanted to introduce those briefly here So now what we're going to have here is that we want to go in and we want to look at the response of first order circuits to time dependent sources. So up to now, we've had constant sources. And since we're going to be introducing time-dependent sources, what you're going to find here is that we have two very, very different processes. Okay, so there are two different sources, right, which would be a constant versus a time-dependent. With different first order equations. So what we've seen in the past is we had first order equations that looked like this, where on this side, this guy was a constant. And when we solved these guys here, these had very particular solutions. We saw that these guys had solutions that look like this. Right? Very clean solutions. Now what you're going to find here is that we don't have a constant source, but our first order equation looks like this now. It's still going to have this form, but now we're going to have a function of time. And this guy is not a constant source. It really pains me when there are people that what they're going to do here is that they're literally going to go in, and what they're going to do is that they're going to try to write a solution for a constant source for a solution that's time dependent, right? So this is clearly, this is a time dependent solution. They are not the same solutions here. So you gotta be really, really careful. Okay, so there's two significant changes here. Okay, so let's look at the first one. So the first one here is that for a constant source, we already know that the solution must look like this, which I've already written at the top, but I feel the need to keep reminding some of you that that's what that solution looks like. A time-dependent solution, it does not look like this. So what we find here is that for time-dependent sources, the complete response causes more time if converted into a Norton Thevenin circuit. It just costs you more work to convert it into a Norton-Thurton, Thevenin circuit, and then try to do that. My experience is that it's more time efficient to always derive the first order circuit. The first order equation, not the circuit. First order equation every time. And that's what I'm going to do. And what you're going to find here is that there are really only 3 sources that we might encounter. Three possible sources in this course. And what I'm going to say here is that there's this thing called the effective source. Why do I call it the effective source? Well, it doesn't have units of voltage, let's say, or current. And so what you're going to see here is that I could have K1 plus K2 times T. So what that will give you here is that could give you a triangular wave, or you could have more constant, more complicated ones. You could have exponential sources. Let's say it looks something like this here. And I can also have sinusoidal sources. Or, of course, I could have written this as cosine omega. So the sources are now changing, but these are the most common ones. So what that tells us here is that what I'm going to do here is that I'm going to change my language. And I told you that I would do this back in the last chapter here. And, you know, if I would have loved to have kept this language in the previous chapter, but mathematically, it doesn't make any sense to do that. For these kinds of equations, it makes a lot of sense to do this. So what you're going to see here is that the second thing here is that there's going to be a change in language. So now there's going to be a change in language from constant to time-dependent solutions. And what we said here is that this is what we did before. So before here, we had something like this. Let me move this down a little bit because I think I need the space. So we've already talked about x equal to infinity plus xc of 0 minus x infinity times e to the minus t over tau. In this language, what do we actually see here? Well, what we see here is that this guy is what we call the force response, and it's very common to call that the natural response. This language is in the language of, this is what we used for a constant source. But what you're going to find here is that when I look at the complete response now, I want to change it. I want to come here and do this. Oops, let me not do that. And it's going to be 1 minus e to the t over tau. And what you find here is that this is the change in language. Instead of using the constant source language like this, just because it was mathematically nicer to do it, I'm going to call this the natural for a timed solution. And then what you're going to see here is, even though this is true for a constant source, it looks like this here. So remember, this is also true for a constant source. So I'm changing the language. And the reason why, I mean, I told you that the second one, the one in green, that this was my favorite interpretation because it's the language of differential equations. But when you solve circuits, it looks like the one in red up above here. So it's not, it may seem like it's not a big deal to change the language, but it is, especially when you have time-dependent sources here. And what you're going to see here is that now that we're doing this, I want to go in and show you how I want to change this thing. So now if I interpret the time dependent solution, what you're going to see here is that if I interpret the time dependent solution, it's the time dependent source that drives the circuit behavior. When I look at the constant source, what drives the behavior of the circuit? Well, it's the constant source. But the time-dependent source will then force the force response to behave exactly the same way. So, in other words, the functional shape of the force response is completely determined by the time-dependent source. Okay, and this is a big deal. Physically, it has to be this way, and mathematically, it's exactly this way. So when I look at the time-dependent source solution here, right? So when I look at the complete response, for a time source, I'm going to get x of t, and then look at what I'm writing now. I'm going to have my natural response right here. And this is what you guys call in differential equations your homogeneous solution. But now I got to look at the force response. And what you're going to find here is that I'm going to have x forced of t. This guy, this is what we call our force response. You know, I should be a little bit more careful. I shouldn't put a d there. This is our force response. And what I'm saying here is that this guy right here, this guy is how do I say this? Must have its functional form the same as the source. It must have exactly the same time dependence as the source. I mean, think about it, right? So physically, if the source is sinusoidal, then the capacitor slash inductor must behave sinusoidal. If the source is linear with respect to time, then the current in the capacitor must be linear as well. They have to have that functional form here. So if I go and I write this mathematically here, then I'm saying this, that so if I look at my solution, my first order equation, which looks like this, right? This guy right here is my effective source. So that means the source lives in this guy. So then if I have a source that looks either something like this or like that, then this tells us immediately that the force response, right, must be the shape of B1 plus B2t, B1 plus B2 e to the minus at, where B1 and B2 are just constants to be determined from the differential equation. So my force response must be exactly like this here. So what you're going to find here, I'm going to just sort of like verbally tell you what we're going to do here so that you get a sense of where I'm going with this. Because once I start, you're going to see things are going to move really, really fast. Okay? So what I want to do here is that I just want to say it nice and slowly and see if you can hear what I'm saying. Okay? So what we're going to do here is that we're going to start off and we're going to derive the first order equation using simple circuits. And our primary way is KCL or KVL or a combination of the two. And then what we're going to do here is that we want to check our differential equation to see if it's correct. Now I got to be careful when I say that. I want to do a simple check. That means I want to do a check to first order approximation. We should be able to see what the steady state solution looks like. That means, what does t equal infinity solution look like? Okay. From the first order equation, we're going to write down a general complete response. That means that what we're going to do here is that we're going to have an arbitrary constant. So we have to write down our solution that has an arbitrary constant. Then what we got to do here is that we got to go in and we got to solve for our constants for the force and response. That's what I call the B's. And you're going to see that the homogeneous solution is going to have a constant A. These are arbitrary constants. B1 and B2 are not arbitrary. I should be careful with my language because it's the differential equation that actually tells you about that. So once I have my forcing constants, then I solve for my initial condition. Once I have my initial condition, that's going to fix the arbitrary constant A. And then I'll be able to write the complete response. That's what we want to do right there. So what I want to do here is that I want to go in and I want to show you my problem solving strategies here. Okay. So let me set this up and then we'll be good to go here. So this is a lot. And so what you're going to see here is that I'm going to come in and what I'm going to do is that I'm going to share with you what I consider my strategies. And then from there, of course, we're going to go do 3 examples. Okay, so here we go. So the first thing that we're going to do here is that if we have a capacitor, we're going to need the capacitor equation. If we have an inductor, you're going to need the inductor equation. Okay, so the first thing I'm going to do is I got to derive the first order equation. And so simply what you got to do here is you got to connect, depends on what you're talking about. So what I'm really talking about right here, look at that. I have to write an equation that contains x and dx dt. So if I have a capacitor equation, I need an equation that contains Vc and Ic, which is of course C dV dt. If I have an inductor equation, then I gotta write an equation that connects I and VL, I of L and V of L, which is of course this guy right here. So we create a first order differential equation by connecting VC and IC, IL and VL. Then what we do here is what I call proper form. Do you have to do it this way? Not really. There's multiple ways of doing this. I mean, there's a lot of times where people actually do Laplace transforms. Are Laplace transforms okay? Yeah, of course they are. You just better make sure you know what the hell you're doing. Okay? And so when I say proper form, that means that you isolate the derivative term. And here's a word of warning that's not in here. Okay? So I'm going to say warning right here. Ooh. I just wrote warning. There should be no minus sign on the left hand side of the first order equation. I've seen a lot of people come in here and this plus sign is a minus sign. If you do that, you know you did something wrong. Go back and do it all over again. Go find that minus sign. Very, very important. No minus sign ever goes there. Once you derive this differential equation, you should do a simple check. You need that simple check. Check to see if the steady state solution matches your differential equation solution. And I'll show you how to do that. It's not a very hard thing. Does that mean that your differential equation is correct? Nope. It does not mean that it's correct. But it's a nice simple check to see if you're at least headed in the right direction. Okay. So here we do step 2. You want to derive the general response. So that means you're going to write x of t is going to be the natural plus the force. And then immediately you're going to write this right here. You're going to have your A e to the minus t over tau, and you're going to pick your tau off right off that differential equation right there. You can see that the second term has 1 over tau. And then you're going to write out all of the possible force response solutions. And so here I only wrote 2. So remember the force in response. The force in response looks like the source. And then to solve for B1 and B2, I got to sub them back into my first order equation and then set up 2 equations and 2 unknowns to solve for B1, B2, and possibly B3. Okay? Again, the natural response, I just pick off the time constant from my differential equation, which is right here. And then I have that. So now I have a complete response. So that means when you're done here, okay, when you're done, the only unknown constant is A. You've already solved for B1 and B2. Okay. So then we got to go solve the initial condition. This is a chapter 6. This is a chapter 6 problem. We got to go solve for the IC, either VC of 0 or IL. And then we have to apply that initial condition to our general complete response. Once we do that, we now have the complete solution, and then we got to go solve the circuit. So I will try to be as systematic as possible here. So here we go. I'm going to give you an example. Okay, so here's an example circuit. And what we want to do here is that we want to determine VC of t for minus infinity t to plus infinity. Okay, and here we're going to say that there's an initial condition of 4 volts on the cap. So what does my circuit look like? Well, my circuit's going to look like this here. My circuit's going to be 10 sine of 20t u of t volts, and then I'm going to have a 10 ohm, then I'm going to have a capacitor. And this is a 10 millifarad cap. And our whole goal, of course, is to solve for the voltage of this capacitor right here. Now, is that not the easiest circuit you've ever seen, right? You have a source, you have a resistor, your capacitor. Man, dude, this is in Thevenin form already, right? You must be happy. Yeah, we'll see about it. Okay, here we go. So we want to do this here. So here we go. So what we're seeing here is that I'm going to go through the steps. First thing that we want to do is that we want to derive the first order equation. Right? That's the first thing that we want to do. So what am I going to do? Well, this is a series circuit, so I should apply KVL. Because if I applied KCL, it doesn't give me it doesn't tell me anything. Okay, so because this is a series circuit, apply KVL. So what I'm going to do here is that when I look at my circuit here, what you're seeing here is that we know that there's a current that's going to be dominated by the capacitor. It's the capacitor that's going to tell us how the current here. So if I apply KVL, we can clearly see here is that we must have a polarity on that 10 volt that looks like this. So here I go. So I'm going to write KVL says it's V source has to be the voltage across the 10 ohm plus the voltage of the cap as a function of time. Because the resistor is in series with the cap, we could then come in and just say, hey, the voltage across the 10 ohm resistor should be R times the current of the cap. And so when I write this down, you could see that then this guy has to be what? It has to be R IC plus VC. Check out the equation. Look what I just did here, right? This equation contains VC and IC. That's what we wanted. So now the next step here is that to get it into a differential equation, apply the capacitor equation. So if I apply the capacitor equation, here's what I see here. I see that I have you know what? Instead of the R, I'm going to put 10. So I have 10 IC plus VC, but now IC should be VC dt. And when I look at this guy, the C value is 10 millifarads. So this should be what? 1, 2, 3. This is going to be 0.01 dV dt. So if I plug that in, I'm then going to get what 10 times 0.01 is going to give me 1/10 dV dt plus Vc. And this guy has to equal the source, but we already know that the source is 10 sine of 20t u of t. So now, if I look at this, it's not in proper form. So now what I'm going to do here is that I'm going to write this in proper form. And the only reason you would write this in proper form is because I assume that you're just going to follow the way I'm going to do this. That's the only reason why you would do that. So now look what I'm going to do here. So if I do this, what I'm going to get here is I'm going to get VC dt plus 10 VC equals 100 sine of 20t, of course, times u of t. So it looks like this here. So what I'm going to do here is that look what you're finding here. What you're finding here is that look at the way the 10 is. We are not interested in what's right here. We want this in the form that looks like what? We want the tau to be in the denominator right here, not in the numerator. So what I'm going to do here is that I'm going to say that this is not in proper form, but first of all, I typically don't care about this, but to be technical, we should write this as VC of t plus VC, and this will be 1 over 10 equals 100 sine of 20t u of t. So now I can see right away that my tau value, nope, we're not interested in tau, we're interested in 1 over tau, is then going to be, it's going to be 10. Okay, so now that we have that, we could then go in and start to deal with this thing. So the way I'm going to look at this thing here is that I'm going to do the following thing here. So then I'm going to go to step 2. What I want to do now is that I want to derive the general response. And when I say the word general response, that means that you have a solution with constants A, B1, B2. And these constants have not been solved for. Okay, so we want to derive the general response to the best of our ability. So here we go. So what I do here is that I do the following thing. Is that my job here is that I do the following thing here. So I'm going to say here is that the general solution or the general response is then has to be VC of t. There has to be a natural response, and there has to be a force response. So instead of writing this like this, I'm going to write it like this now. And so when I write this, my natural response looks like that. And my force response should be, because this is a sine function, it has to be a linear combinations of sines and cosines. So then it's going to be B1 sine of 20t plus B2 cosine of 20t. So right now what you're seeing here is that this guy right here, of course, is my natural response. This guy right here is my force response. That's my general solution right there. So this is just like immediately you write this down. So the first thing that I would probably do here is that I would determine 1 over tau right away. So the first thing that I do is that I do this. I would determine 1 out of tau from looking at first order equation. And so what I'm saying here is that I'm going to look at my first order equation and look what I'm seeing here. I know that the first order equation must look like this. Its functional form must look like this. And what you're seeing here is that this guy is what I'm looking for. I'm actually looking for that guy, 1 over tau. So what I do here is that I compare with dv dt plus 10 vc and what you're seeing here is that you could see that 1 over tau has to be 10. So this implies here that 1 over tau should immediately be given the value of 10 hertz. So now I have my time constant. Okay, so I immediately know what my time constant is. So that's the first thing. So what I did here is I just determined 1 over tau. The next thing that I have to do here is that I have to determine the forcing constants B1 and B2 from the first order equation. So how do I do that? Well, these forcing constants, the way you do them is you substitute your forcing response into the equation here. Now, one of the things here that you gotta be careful here is that I think we should do this once so that we do that. So note that the first order equation has 2 solutions. So the first solution is the natural response. And I think you guys call it the homogeneous. homogeneous solution. So what that means here is that if you were to substitute this guy, so if you were to substitute this guy into this equation. So if I took n solution here, and I put x of n, which is a e to the minus 10t, if I put that into that equation is 0. Let me show you what I mean here. Because in our equation, it's got to be d dt of a e to the minus 10t plus 10 a e to the minus 10t here. And if I take the derivative of that, look what I'm going to get. I'm going to get minus 10a e to the minus 10t plus 10a e to the minus 10t. So this will always give you the homogeneous solution. We do not care about the homogeneous solution. We care about the forcing constants, B1 and B2. So what we really need to do here is we need to substitute in the forcing solution to get B1 and B2. So what I find here is that a lot of people will come in and they'll put both of these solutions in here. But if you put in the natural response, you'll always get 0. So 0 always equals 0. But what we want to do here, doing that does not help you get B1 and B2. So what we do here is so the forcing solution to get B1 and B2. So what you do here is that now you want to sub the forcing response into the first order equation to determine B1 and B2. So here we go. So what's my first order? So I have V forcing dt plus 10 VF. Now I'm going to say that VF, of course, is B1 sine of 10t. Wait, is it 10 or is it 20? I think it's 20, not 10. It's going to be 20t, B2, cosine of 20t, and then here we go. I'm going to substitute them in. So if I do that, what am I going to get? Well, I got to take the derivative of this term right here. If I take the derivative of this term, if I take the derivative of sine, I'm going to get what? Well, I'm going to get 20, and then the sine turns into a cosine, so I'm going to get B1 cosine of 20t. Now I got the second term. If I take the derivative of cosine, I get negative sine. But note that then I get 20, which I already factored out, is going to give me minus B2 sine of 20t. So this term right here is what? dVf dt. Now let's look at the second term. If I look at the second term, what does this look like? Well, it should be 10 times the solution, which will then be B1 sine of 20t plus B2 cosine of 20t. Now, what I'm going to do here is that I'm going to move this actually over here because I'm running out of space. So I'm going to move this guy down here, but it's the exact same equation here. Come on, baby. Let me see if I, oh man. Let me try moving it again. So I'm going to move it to right here. And what I'm seeing here is that this must equal, so let me be careful here. So this guy here is 10 V forcing. So then the right side should be equal to what? It should be equal to 100 sine of 20t. So note that this guy right here is our f of t. our effective source. But one of the things that you should really pay attention is that look at the left side. The left side is a combination of cosines and sines. The right side is a combination of only sine. So to help here, look what I'm going to write. I'm going to do 0 times cosine of 20t. Of course, that is still 0 and that doesn't affect this thing. So what we got to do here is that we now have to solve these equations for B1 and B2. So the only way this solution is valid is if the right and left sides have their sines and cosine cofactors equal each other. So look what I got to do. I got to collect all the sines and all the cosines. So let's look at the sine 20t terms. So let's go do that. So if I do that, check this out. Here's a sine, here's a sine, here's a sine. So if I look at that equation, then this tells me here is that the first term is going to tell me that this is going to be minus 20 B2, that's the first term. The second term is going to give me plus 10 B1. And then my right-hand side tells me that it must be 100, but I'm really multiplying this whole thing by the sine of 20t. Let's go to the second one now. I look at the cosine 20t terms. And these guys, I'm going to pick with the purple. And so when I do that, I'm going to look at only the cofactors now. So if I look at the purple terms, it's got to be 20 B1. The second term is going to be 10 B2. And then you could see that the right side is 0. That's the cosine of 20t terms. So what I'm doing here is I'm setting up a 2 by 2 matrix for B1 and B2. This sets up a 2 by 2 matrix solution. So now if I look at the matrix solution, it's going to look like this here. So I'm going to take all the B1s, right? So the B1s are going to be 10 and 20. And then I'm going to take all the B2s, which will give me minus 20 and 10. And then I'm going to get 100 and 0. So then, of course, the matrix magic. This is going to give me a B value of 2 for 1, and B2 is going to be minus 4. So I now have these guys here. I can finally write down my complete response, the general response to this. So the general response now looks like VC of t, which will be the natural plus the forced, and this should be a e to the minus 10t, which we already caught our tau. And then if I put these values in, it's got to be 2 of sine of 20t minus 4 cosine of 20t. Now I have my general response right here. So I can then come in and say, this is the guy that I have to worry about right there. Okay, so now what we're going to do here is that we're going to go to step 3. So in step 3, what we're doing here is that we need to go and solve for VC of 0 minus and determine the integration or arbitrary constant. A. Okay, so if I do that, well, we don't have to solve the initial condition. Why? It was given to us, right? So we were given that VC of 0 minus was 4 volts. So I'm now going to apply this. Given this, we're going to apply this to general response and determine A. So here I go. So I'm going to write VC of 0 minus is of course 4. But that then means then I have A e to the 0 plus 2 sine of 0 minus 4 cosine of 0. And of course, this tells us then that this will be A minus 4. We can clearly see here that we now have that A must be 4 plus 4, which will give us 8. So what am I going to do with that? I'm going to plug it right back into my solution here. So now I know that with all my constants, A, B1, and B2 being solved, we then say here that the complete response is then VC of t, which will then be 8e to the minus 10t plus 2 sine of 20t minus 4 cosine of 20t. And that's my voltage right there. This is how the voltage of the capacitor behaves right here. So what I'm going to be asking you is that I'm going to be asking you to solve this problem and then go and plot it. So what I did here is that I went into PSpice and I plotted this thing. So a lot of the times you're going to see me say, now interpret your solution. So what I did here is that using PSpice, VC of t was plotted. Unfortunately, I didn't convert this guy, which I should have, but it looks something like this here. It's in black, unfortunately, which is terrible. And what I'm going to do here is that I'm just going to come in and sort of like highlight it so that you could see it a little bit better. Apparently, I was not very clever in making sure that I didn't convert this into white to black and vice versa here. So here's the solution, the steady state solution, that is. And what you find here is that I went in and I started to look at this guy here. So the first thing that I did here is that I started looking at the solution to this thing here. So let's look at various points. So the first point that I looked at is I looked at VC of 0 minus better be 4 volts. Well, is it? Well, it better be at 0 plus. So if I look at the 0 plus solution, of course, this is e to the 0 plus 2 sine of 0 minus 4 cosine of 0, which is, of course, going to give you 8 minus 4, which is 4 volts. So when I look at my plot here, what I see here is that this plot tells me that it starts here and it goes from here, and then it starts to move all the way up like this. And what you find here is that this point right here is 4 volts. So I could see that at t equal to 0, it's exactly 4 volts, and it's exactly what we expected here. Now, another thing here that I wanted to look at here is that I noticed that the cap's voltage oscillates with angular frequency of omega equal to 20 rads per second. Now, how do I know that? Well, look at the solution. If you look at the solution here, you could see that this guy has an angular frequency of 20. So then I said, well, if that's true, what is the period? So what is the period of the cycle? Well, I know that the period, well, I know that the angular frequency must be 2 pi f, and this guy is 20 rads per second. So then this tells me here that the frequency has to be omega over 2 pi. So if I plug this in, you could see here that that's 20. So then I'm going to get 10 divided by 10 divided by pi, which will then gives me 3.1847 hertz. I know there's a lot of sig figs there, but I'll reduce it right now, but I wanted to be careful because PSpice gives you so many sig figs. So here I go. Look at the period now. We know it's 1 over the frequency. So if I compute that, I get 0.314 seconds. So in other words, I know what the frequency is. What the period of the cycle is, like that. So guess what I did? I went into PSpice and I actually measured this thing. And so when I measured this, I measured the time period, the time from here to here, and PSpice comes back and says that the time is 3136 seconds, which is the period. So if you compare the PSpice value, right, this is PSpice, compared to my value, this is 3.14, and I'm getting 3.14. They match exactly to 3 sig figs. And then I went to go here and I tried to just pick an arbitrary point. And so the point that I picked here is that I picked, so now what I'm going to do here is that the next thing that I did here is that I'm going to pick an arbitrary point to check solution. So what I did here is that I went in and I picked at a time at one of the peak values. So if I looked at PSpice right here, if I come up to my curve, what you're going to see here, this peak time right here, this has a time of 2.0183 seconds. So at that peak value, that's what I'm going to, that's the time here. So I'm going to say here is that the peak voltage is T equals to, what was it? I think it's 2.0183 seconds. Is that right? Yes. So then that means I want to check to see what that voltage is. So then I'm going into and I'm going to say VC at T equals to 2.0183 seconds is then going to be equal to what? Well, it's got to be 8e to the minus 10 times 2.0183. And then I'm going to get 2 sine of what? 20 times 2.0183 minus 4 cosine 20 times 2.0183. And then I just punch this into my calculator. And what I see here is that this number turns out to be 1.37 times 10 to the negative 8. And then I get 0.914 minus 3.558. And what you're seeing here is that this number right here is the natural response. And that means here is that it has decayed from its natural response. And you could see that the value is quite small, 10 to the negative 8. Wow, that's like nothing, right? That is like nothing. And then this term here is the force response, and that should be the peak value. So when you look at this value, what you're finding here is that I'm essentially ignoring that, and then I get a value of 4.472 volts. So this is what my solution tells me for this. So then I went in and I said, what does PSpice tell me? So when I go to PSpice, I come up here and PSpice tells me this here. PSpice says that the peak voltage at this time right here is then 4.4701. So when I compare the PSpice value to this value, so if I look at VC of PSpice, I then going to get a value of 4.4701 volts, and you could see the 3 sig figs, they're exactly the same, and I think that what ends up happening is that there's rounding that I did that actually does that. So what you're seeing here is that, man, that's a fairly simple circuit, if I might remind you here, right? Look at that circuit. Man, that's a nice circuit right here, right? You could take that circuit home to mama and show her that this is a nice circuit. But the fact is, they're a lot more complicated than that. And we didn't even calculate the initial condition. We didn't even solve the circuit problem. Now, you might agree at this point that when I say this, what am I really telling you right here? Have you heard me say that you better respect these homeworks? Because let me tell you, you will never see a circuit this nice from me. Can I be any more clear than that? Okay, so I know you don't trust me, so I figured we should just get cut to the chase, right? Let's go do our first example, okay? Let's go do our first example. So if we do our first example, here we go. We want to apply this whole process to this circuit right here. right? Here we go. Here's our circuit. And note, no initial condition. That means you got to go in and you got to solve that initial condition. So there's already a complexity here. And note that this does not say the current of the inductor. It wants the voltage of the 24 ohm resistor. So there's a lot more work now that's involved here. So let's go do it. Okay. So what we want to do here is that, as always, we want to know what to expect here. Okay. What should we expect? Do you think, so the first question says, describe the behavior of the inductor's current. So is it storing or is it decaying current? Right? So the first question is, you're looking at that circuit and you're probably going like, oh my gosh, this is crazy. The first thing that you should be thinking here is that you want to simplify the circuit. Is there anything in series and parallel? Well, the first thing that I see is that I see source transformations. Okay. If I look at source transformations, we got to be careful about what the switch does. So right now, you're seeing two things here. Okay. So the first thing that I want you to realize is note that the exponential source doesn't turn on to t equal to 0. Okay. So what I'm looking at here is that at t equal to 0 minus, the e to the minus 5t source is not on. So what I really see, right, remember, always try to understand your circuit before you start. So when I really look at the circuit, this is what I'm seeing. I'm seeing a 24, an inductor, and I'm seeing a 32 volt source here. Okay, here's my 24 ohm. Here's my 8 Henry inductor. Look at the switch. It's open. So then I come over here and then I have this guy right here. So when I'm looking at the circuit here, what dominates the inductor here? Is it the 32 volt source or the 5 amp source? It's the 5 amp source. How do I know that? Do a source transformation. If you do a source transformation, look what you get. What time is it? Okay, I got 2 minutes. I get something like this. And then I'm going to get what? I'm going to get a resistor, and then I'm going to get a source. So this is going to be a 6 ohm, and then the source here is going to be a 30 volt source here. Right? It's going to be a 30 volt source. So what I'm seeing here is that the 5 amp source is not going to dominate, right? So what I'm seeing here is that the effective source acting that inductor is a 2 volt source here. And so what I'm seeing here is that the current that's going to be flowing through the inductor has to be in this direction right here. Let me make sure that makes sense right here. I have two opposing. And then what I expect here is that I expect that the circuit is, so then what's going to happen here? When the switch is thrown close, so now what I'm going to do here is that at t t equal to 0 plus, we're then going to kill off the 5 amp source, which then is going to allow the inductor to do what? To increase in current. So if I calculate a current source, I mean an inductor current that shows that it's decaying, you know there's a problem. Go back and fix it. Okay, my whole goal on Wednesday is to do what? Do 2 examples. I don't know if I can do 2 examples in 1 hour, hour and a half. So I'm going to come in, I'm going to be busting, right? I'm going to be busting. And guess what? The other one has a dependent source in it. So it's involved. So I'm pretty sure homework and quiz is going to be next Monday. So it's going to be a little mini exam on Monday. And also, I'm going to be at Cabrillo today at 2 o'clock to pass out function generators and the other oscilloscopes that I have. A lot of these function generators are not working. So if you have a function generator that doesn't work, come and get me, and I will give you a function generator so you could use it till the end of the semester. Okay, I'll be in the physics lab room. I'll send out an announcement as soon as I get out of physics 4A. Okay, I'll talk to you guys later, man. See you later.